What is a function? There are a few concepts related to the notion of function that can get confusing. Strictly speaking, they all have a very precise definition, but in some contexts, we relax those definitions, we abuse notation, and we use the terms to mean something slightly different. Sometimes students may learn the same theorem in two apparently contradictory ways, depending on whether it is in a calculus class or in a linear algebra class. But there is no contradiction if we understand the conventions. In this sequence of videos, I will do two things. First, I will explain the proper use of these terms when we want to be strict. Second, I will explain the conventions used in calculus to relax those definitions. If you have taken a logic course, perhaps you have learned the definition of function as a subset of a Cartesian product. What I will write here is equivalent, but in plainer English. A function consists of three pieces. First, a set of inputs called the domain. In this example, the domain is a set A with elements 1, 2, and 3. Second, a set of potential outputs called the codomain. In this example, the codomain is the set B with elements 4, 5, and 6. And third, a rule that matches each input in the domain to exactly one output in the codomain. In the picture below, I am representing the matches with arrows. Notice the notation I am using. I am giving a name to the function, in this case f. Then, for each element x in the domain, I am calling f of x the corresponding element in the codomain. So the name of the function is f, not f of x. F of x is an element in the codomain, not the name of the function. Back to the example. There are only 3 elements in this domain, so I can just list all the matches. F of 1 is 4, f of 2 is 4, and f of 3 is 6. That's the rule. In most examples, however, I will have an infinite domain, and I won't be able to list all the matches. Instead, I will probably describe the rule with an equation. Why did I refer to the elements in B as potential outputs? I want to distinguish between codomain and range. The codomain is the set of potential outputs. In this example, it is the set 4, 5, 6. The range is the set of actual outputs. In this example, it only has 2 elements, 4 and 6. The codomain is a set we determine beforehand from which we are allowed to choose outputs, and then, once we define the rule, we find we are only using some of the outputs, and those form the range. Notice that to define a function, I only need to give the domain, the codomain, and the rule. I do not need to explain what the range is. The range can be calculated from the rest of the information. Finally, one piece of notation. If you read an expression like this, f colon a arrow b, it means that f is the name of a function, a is the domain, and b is the codomain. It is just shorthand for all of that. For example, I could define a function f with domain all the reals and codomain all the reals, with the rule given by the equation f of x equals 3 plus x squared plus sin x. So far I have explained the strict way to define a function and to refer to its components. Next, I will explain some conventions. You may be thinking, in calculus or in precalculus, I am used to defining functions in a much easier way, just by giving the equation. For example, I may say the function g is defined by g of x equals 1 over x squared, and say nothing else. We do this all the time. Is it okay? There is a convention we use in single variable calculus. We agree that it is okay to define a function by just giving the rule, normally as an equation. And then, by default, we assume that the domain is the largest subset of the reals on which the rule makes sense. And we assume the codomain is all the reals. For example, when I define the function g by the equation g of x equals 1 over x squared, if I do not say anything else, implicitly I mean, for which values of x does this equation make sense? I can divide by any non-zero number, so x can be any real number except for 0. So that's what I mean, the domain is all the real numbers except for 0, and I also implied that the codomain is R. This convention is useful because we are only talking about this specific type of functions. It saves a lot of time. But once you move to other fields of math, like abstract algebra, where the domain and codomains may not even be sets of numbers, then you will have to be careful and specify domains and codomains to define a function. There is a second convention worth mentioning. Look at these two functions. Are they the same function? Strictly speaking, they are not the same. They have the same domain and the same rule, even the same range, but they have different codomains. They differ by the element 5. In practice, particularly in calculus, we often abuse notation and pretend that these two functions are the same function, and use the same name for both. Effectively, we treat the codomain as irrelevant and we only pay attention to the range. If you had never heard the word codomain before, this may be why. I will talk more about this abuse of notation in the later video about surjective functions. But remember that in other areas of mathematics this distinction may be important, and in that case we will stick to saying these two functions are different. To make matters worse, this notation is not universal. The names I have introduced here are the most commonly used names in math, but sometimes people use different names, at least in some areas of computer science. They still use the word domain the same way I have. But what I have called codomain, they call range. And what I have called range, they call image. This makes it confusing because now range may mean two different things depending who you ask, but don't blame me. The moral is that if you're working on math with somebody else, you should make sure you agree on notation so that you can understand each other.